Okay, good, great. So I think we have completed the first part of this, so to speak. I think we did till what? Till about, if I remember right, we did some tensor products and things like that, right? Did we do the C naught gate?
Yes.
Yes, we did the C naught gate, right? And I think, yeah, so we've done till. So today we will actually try and get into more, a little more complex gate, quantum gate called the Hadamard gate, and hopefully, yeah, they're just trying to switch on the TV. Yeah, don't worry about that. And then we'll probably talk a little bit about something called the Oracle Deutsch problem, the Deutsch Oracle problem, which is probably a simple problem where we will see how a quantum computer can outperform a classical computer, right? So that's what we'll do. So anybody has any questions on what we did last time? Should I take 5 minutes to review it, or you're all comfortable? What's the state here? Guys, you tell me something. Okay. The only answer I got was from Shrikant, so I'm going to start with the new. So I've never understood why people don't speak up, but that's fine. All right, so we're going to get into qubits now. So we all talked about how we work with C bits, right? So you basically, you have the Dirac notation where you kind of represent zeros as 1 0 and 1 as 0 1, right? It is the Dirac notation that you kind of do that. Now, what I'm trying to tell you is we actually use this is a C bit, right? This is how you kind of show a classical bit. So the same way you can actually talk about a qubit also. Okay, the same notation. So finally, what we will see is that the classical bit vectors we've been using are just special cases of qubits or quantum bits. A qubit can also be represented by A, B, where A and B are complex numbers. That's the only important thing. Why are they complex? Let's not worry about it right now. That's a whole other derivation that we will see. But you can represent a qubit as a complex number instead of as a real number, right? And with the condition that the square root of the magnitudes of your complex numbers equals 1. And this is what you can take as the probability. Right? So the C bit vectors are written as 1 0 and 0 1, whereas your quantum bits are in superposition, right? They are in. So I talked a little bit about superposition. Anybody have an idea what it is? What is superposition?
Actually, it is the state of a qubit.
Yeah, so when you talk about a classical bit, the way we understand classical bits is a classical bit exists in either state 0 or state 1. Whereas quantum bits, we understand them to kind of exist in both states, in both 0 and 1 till observed. When you observe, we kind of think it as collapse into either a 0 or a 1. That's kind of the way you think about a quantum particle, right? About a qubit. Now, I have to tell you that this particular way of looking at it is known as the Copenhagen interpretation. Okay, it is kind of called the Copenhagen interpretation of quantum theory. It's not the only theory. There are other theories also, but we will not get into that. For now, we will stick with the Copenhagen interpretation, which just means that they exist in both states. And once you measure it, it kind of becomes, you observe it in one state. So what does 1 by root 2 or 1 by root 2 means? You can think about these numbers as probabilities. Because what you're saying is, what this tells you is the qubit can collapse to a state 0 with probability of 1 by root 2 whole square, which is half. Similarly, you can say that the qubit, the probability that the qubit collapses to the value 1 is 1 by root 2 whole square, which is again half. So this basically shows you, I don't know, a coin toss. You can think about it as a coin toss, right? Whether it's head or tails, 0 or 1. But you're basically saying it's a quantum vector. It's a qubit. And the condition being the square of the magnitudes equals 1. Right? The Kolmogorov. Because finally, when you measure it, has to be in 0 or 1. There is no other state. It can be in any state between 0 and 1. So now you can ask me, how do you get these probabilities? Right? Because you can't measure it. The moment you measure, you only get a value 0 or 1. Okay. But we are saying these somehow denote the probabilities of what state it will actually collapse to. But how do you get these probabilities? Right? Anybody take a guess? Yeah, tell me. Correct, but you don't know, right? When you measure it, it comes only 0 or 1. So the only thing is you keep measuring it over a number of times. If you keep measuring over the number of times, the number of times that it actually collapses to 0 or 1 gives you we can kind of understand it as giving the probability. It's not strictly probability, but we kind of interpret it as probability. Okay, makes sense, guys? Similarly, half root 3 by 2. Again, you square it. That is 1 by 4 and 3 by 4. So the probability is 1. It has got a 0.25 chance that it will collapse to a 0 and 75% chance that it will collapse to a 1. Similarly, minus 1, 0. The probability now is it's always going to be a 0 because minus 1 whole square is 1. Okay. Half and minus, same thing. Whether it's 1 by root 2 or minus 1 by root 2, because you're squaring it, the probability remains the same. Right? It's still half. Good. So there is, you kind of at least conceptually get some idea of what are qubits and superpositions and how we kind of describe these things. One way to understand this is polarization. I think all of you must buy sunglasses, right? When you buy sunglasses, they will say polarized sunglasses. Right? Some of them will advertise that these are polarized. What is polarization? Polarization is a phenomena, is a quantum phenomena. Is actually you can think about polarization as the spin of the photons. So basically either this way or this way, 0 or 1. Okay, so some classes are polarized to only let you the horizontal photons in, some only for the vertical one. So you can polarize it either way. So polarization is a quantum phenomena, things like that. Yeah. Yeah. So that is what that is. Maybe Raj, you could push into a screen, or maybe you can see his screen. Okay. Puja mark click count and screen chodochu. You can see your screen. So that is what that is. Okay. So till now, simple. These just denote the probabilities. That's it. Okay. So when I say 1 by root 2, 1 by root 2, I'm just saying it has the probability of half 1 by root 2 whole square or 1 by root 2 whole square to collapse to either 0 or 1.
It will be partly cloudy with a high of 29 and low of 18.
Oh, okay. Somebody said. Yeah, that's machine learning too, I guess. How can a qubit have a value again? It's not 0 or 1. This is called superposition. Superposition means that the qubit is both 0 and 1 at the same time. See, this is a difficult concept to understand. Like I said, there is no middle world or our earth understanding of this phenomena. You cannot. So like I said, it has to be shut up and calculate only. There is no way to understand what does it mean to be both. Okay, it doesn't mean anything to be both. But in quantum states, what you have to understand is, see, the biggest thing that you have to understand in the Copenhagen interpretation is, in our world, we think the observed is different from the observer. That is the fundamental assumption in all our world, right?
Something paradoxical, Schrodinger's cat.
Yes, like Schrodinger's cat or whatever. Like if I see a phone here, whether I look at this phone or I don't look at this phone, the phone remains what it is. That is our assumption. This is the base assumption that gets violated when you get into the quantum world. The observer changes the observed. The moment I see something, it becomes something. And here is where the connection to all ancient philosophies, if you really want to connect. Okay, this is the real connection. The observer and the observed are connected. They change each other. Okay, when I look at this, I also change. The phone also changes. Okay, at our scales, we cannot see it. At the quantum scale, you can observe it. That is what the difference is. That is why it means that it can be both 0 or 1. There's a very famous Buddhist Zen saying, I don't know if you've heard about it or not. He says, if a large tree fell in the forest and if there was no one to hear the sound, did the tree actually fall? So it's the same thing, right? So anyway, when we measure the qubit, it collapses to an actual 0 or 1. We usually do this at the end of the quantum computation to get the result. So qubit has AB, blah, blah, blah. I've said all of this. For example, qubit 1 by root 2, 1 by root 2 has 1 by root 2 whole square, half chance of collapsing to 0 or 1. So it's just a coin flip. The qubit 1, 0 has 100% chance. So this is the same thing that I talked about in the last slide. So this is clear. Any confusion on this? Okay, then simple. Multiple qubits are represented just like multiple C bits with tensor products. We talked about tensor products, right? See, the only other thing is to remove some complexity. Here I have used only the real numbers. See, ideally you should have used the complex parts also. Okay, because a qubit is represented by something called a magnitude and a phase, which is what you represent in the complex world. The magnitude is the magnitude, the phase is the angle. Okay, so A plus IB, whatever. You can take a magnitude and a phase and then, but right now for simplicity's sake, because that just creates a lot more mathematical complexity when you're dealing with it more than anything else. Conceptually, it makes no difference. Okay, mathematically, it's a little more complex. I have decided to use only real numbers to explain this to you. But think about this also having complex numbers, because in reality, these are all complex numbers. Every photon has a phase and a magnitude. Okay. Anyway, so this is the tensor product, and even if you are representing the state, remember that it still satisfies this. Because finally, what this state represents is one of the 4 states that these 2 qubits can be in. So according to Kolmogorov's, I said only Kolmogorov's third axiom is violated. The first and the second don't get violated. According to the second, any event that is certain has a probability of 1. So here, these 4 together are certain, because they are the only 4 states in which the end qubit, the end combination of these 2 qubits can be measured, because this is 1 qubit, this is 1 qubit, and this is the state of a qubit. The state of a qubit can only be in AC, AD, BC, BD. Okay, so you can think about it like, I don't know, 0, 0, 0, 1, 1, 0, 1, 1 type thing. So if you think about it, so that's why it still holds, this inequality is still held, because the Kolmogorov's second axiom is not violated. Okay, it's important to remember that. So for example, same thing, if you multiply 1 by root 2, 1 by root 2, blah, 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 it's all half, 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 half. All the squares of 4 halves are 1 by 4, 1 by 4, 1 by 4, 1 by 4 equals 1. There's a 1 by 4 chance of each of the collapsing to blah, 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 whatever. Okay. So this is, again, not very difficult. I've kept it very, very simple. But please remember, this is an introduction. Whenever I tell you some of these things, I'm forcibly trying, because there are a lot of exceptions to a lot of these things. But at least as an introduction, don't just get worried right now. Okay, just get out of it. So how do we operate on qubits? The same way you operate on C bits, with matrices. You can think about gates as matrices. A gate is nothing but a matrix. All the matrices we have seen also work on qubits, bit flip, C naught, etc. Okay. So similarly, this is the flip operator, right? 0, 0, diagonal 0, 0, 1, 1. So you multiply it, it just flips. It just flips, that's all. There are several important matrices which only make sense in a quantum context. We will see at least one of them in the next few slides. Okay. Like I said, these are all reversible and inverse of each other. All quantum gates have to satisfy, definitely reversible. Irreversible, though, it's not there. We'll see how to write an irreversible gate using reversible quantum gates. Right. This is probably one of the most important quantum gate, the Hadamard gate. Okay. You probably would have heard about this name. Actually, even the cross product is called the Hadamard product. If you have actually, it's actually called the Hadamard gate. He's the same guy who also devised this, who also talked about cross products. But anyway, I won't go there. So what is the purpose of Hadamard gate? It's to do a few things. Let's see the first purpose here. It takes a 0 or a 1 bit and puts it exactly into equal superposition. So for example, you think about how will we actually do quantum computation. You have to first take a classical bit, okay, convert it into your quantum world, do a lot of operations on it, whatever, and finally convert it back. So you take something, you convert, do a lot of things and convert back. That's the way you have to do. So the Hadamard gate is useful to take a classical bit and convert it into a superposition. So that is what this gate is used for. When I say a gate, think about it like a matrix. Like in a classical world, it's the same thing. Okay, it's a matrix with which you multiply. So the gate is this. The derivation of this gate could be a good homework for somebody who is interested, but I will leave it out as a somebody to try it out on their own. So 1 by root 2, 1 by root 2, 1 by root 2, and minus 1 by root 2. Can anybody say why there is one minus sign here? What does it help for? Reversible, exactly. It helps you reverse. If this minus is not there, this gate will not be reversible. That's why there is this minus sign. Okay. So this gate was first done in 1970s actually. Okay, 1970s was when they actually did this gate first. It's very much used. So similarly, just say if you take a 1 0 and if you multiply, it will be 1 by root 2. You can check this. Similarly, you take a 1 and you do it, it becomes 1 by root 2 minus 1 by root 2. So it's basically converting from your, see, this is your bit. This is your gate. It is converting into a superposition state. Similarly, this is your bit. This is 1. Again, you multiply it with this gate. You are getting a superposition state.
In simple terms, can you say they're factorizing it something so that it can reverse it?
Yes, but it is not always factorizable. Andhuka, I'm a little worried about using that term. But yes, but there are quantum entanglement when we get there, you will see that there are certain states that cannot be factorized. Okay, and that is how you can get into. But in theory, something like that. But keep it at this level. This is the right way to think about it. Don't complicate it. The right way to think about it is there is a gate, there is a bit, you multiply, you get the superposition state. That's all. Simple. Okay. Again, guys, on phone, if you do not understand anything, because this is all very simplest of simple things. If you have doubts here, everything beyond it will just seem like some nonsense that I'm talking about. Okay. This is not difficult. The Hadamard gate can do one more thing which is very, very special. It can take things in superposition and convert them back also. It can not only take the bits that are in classical sense and convert it to superposition, it can also take bits in superposition and convert them back into your classical. And that's why this makes it a very, very powerful sort of matrix. It's such a simple matrix, but look at what it can do. Okay. The entire fun of quantum computing is enabled by this simple gate, right? Again, you can check it out. And transform it. This should be unsurprising. Remember, operations are their own inverse. So if you take 1 0, you apply Hadamard gate, you again apply Hadamard gate, you should get 1 0 back. But what is the real advantage is this. We can transition out of superposition without measurement. Because ideally, if I want to know what state, I have to measure. If I measure, I have already collapsed it. Correct. So I can't compute on it anymore. I have collapsed it. But this lets you get to the bit state without actually measuring it. So you can get it and get it back. You can get it, you can keep doing it as many times as you want. Of course, it's all in theory. In real world, there is too much of quantum noise, quantum error corrections, and a lot of other problems. You cannot actually do it so easily. But having said that, at least the mathematical theory works. Implementing it, see, in quantum computing, there are two fields like any other classical computing. There is the software side of it and the hardware side of it. Okay. So right now in our classical world, hardware has become commoditized. Okay. But it has taken many, many years for that to happen. the initial years, if you look at 1940s, 50s, 60s, most of the innovation was happening on the hardware side. So only the software revolution started only late 70s or so. So similarly, right now in the quantum world also, the difficult part is the hardware bit, is building these circuits. Building the circuits is not easy. We can't just build like that. Okay, because the reason is measurement means it collapses, and any quantum system that you build, it will have some connection to the real world, right? It has to be encoded in the real world. So the noise from the real world will keep entering and will keep disturbing every calculation that you're doing. So how do you actually manage that? It's a very, very difficult problem that we haven't yet solved. Okay, we're building toy computers, but real scale computers we don't know how to build. Okay, so anyway, so there is that bit you should understand. We can thus structure quantum computation deterministically instead of probabilistically, because otherwise, till you measure, you don't know what the result will be. Then how can you be sure that you will get 2 + 2 = 4 only? You have no idea. You have to wait till what you get. You may get anything. But here, because of this gate, you can actually control what comes out. And so finally, you know that what is the result that you will get. You can actually get a 1, 0 and then measure it. At that point, you will get 1, 0 only because the probability is 1. But you have to do the conversion before. Okay? Get what I'm saying? Again, I'm pausing for a second because it's an important gate. Hopefully, people have taken in. This is just the state machine, the unit circle state machine, the same thing that we do in classical computing also. Take it like a unit circle, okay, with all the different states, okay, on the unit circle. The left one shows you the negation gate. The right one shows you the Hadamard gate. So think about it, it's very simple. So if you start with a 1, 0, if you put a negation, what will happen? 0, 1. Right. 1/√2 minus 1/√2 negation minus 1/2. Similarly, minus 1, 0, 0 minus 1. Okay. 1 minus 1/√2 minus 1/√2 negation is the same. Similarly, 1/√2, 1/√2 negation is same. So these are called state machines. If you haven't seen them, typically even in classical computing, you do this only. When you're doing computer science engineering, if you build an XOR gate or a NAND gate or whatever gate, you actually write the states and then you do a state machine. This is called a state machine. It lets you, so instead of every time multiplying, you know what the state is. If you put to this what you will go, you can just look at this. Otherwise, every time you take a matrix and multiply it. No? So people don't do that actually. And a lot of your calculators are also built on state machines only, if you really think about it. And a complex state machines, but still a state machine nevertheless. Similarly, this is the Hadamard gate, right? If you have 0, 1, it will get to 1/√2 minus 1/√2. So similarly, again 1/√2, 0, 1, minus 1, and this. So it's just the Hadamard gate and the negation gate. Now we will get to the real complex one. How do you do it with, okay, anyway, let me not talk, let me go. So this is how you can do calculations, right? So to give you an idea, you start from 1, 0, you kind of put a negation. So you get to 0, 1. From there you put a Hadamard gate, 1/√2 minus 1/√2. Again a negation, minus 1/√2, 1/√2. Again Hadamard gate, whatever. 0, and then a negation, minus 1, 0. So it's just to tell you how you can actually put these operators together to create some sort of a computation. So you're getting from 1, 0 to minus 1, 0. Actually, it doesn't mean anything because both with probability 1, it will collapse to 0 only. Right. So you do all of this. This is practically an identity function. After doing all of this, what you have achieved is an identity function. You take 0, you will get 0 here also. But it's just to tell you that you can do fun things. Now you can think it's like a Lego. If you keep adding, you can do all sorts of things.
So it's a negational identity.
No. What you are achieving is the identity, right? Because this is 0, right? 1, 0. Because 1, 0 just means with probability of 1, it will collapse to 0. Correct? What is minus 1, 0? That also is 0 only because minus 1 whole square is what? 1. So with probability 1, it will collapse to 0 again, right? So if you measure this, what the answer you will get is 0. If you measure this, the answer you will get is 0. So but you did all of these other sort of functions in between just to show you that you can do all of this and not change anything. So what I'm saying is the end result is identity. And to achieve that, you used a combination of negations and Hadamard gates. Makes sense, Pawan? Pawan, right?
Yes. Yes, Srini, yes.
Yes.
Thank you.
Hey, no problems. Just if you don't understand, feel free, because this is not. It's not like I have a time constraint. I need you guys to understand more than the time. So recap. Okay. Very simple. C-bits are just a special case of qubits. Qubits can be in superposition. Multi-qubit systems are tensor products, just like C-bits. Matrices represent operations on qubits. The Hadamard takes 0 and 1 to equal superposition and back. We can think of qubits and their operations as forming a state machines on the unit circle. Actually, it will be a unit sphere if it's true complex numbers. I'm just showing you a circle here because it is real numbers, one dimensional. Right? If you have a plane, then you will need a sphere to actually represent the same thing. That's also one of the reasons it gets difficult to show it on a sphere. And that sphere, that sphere has a name. It is called Baloch sphere. Baloch. Okay, it's important because if you say you've gone through quantum computing, somebody will ask you, do you know what is a Baloch sphere? A Baloch sphere is nothing but exactly this state machine. That's all that there is. Okay, on your unit sphere. I showed it on unit circle. That will be on unit sphere. That's all. Okay. Now we are getting to an interesting part. It's called the Deutsch oracle problem. Okay, it is the simplest problem because till this time I told you something about quantum computing, but you guys must all be thinking, what the hell is this actually useful for anything? So this is one problem where we will hopefully try and prove together that a quantum computer can actually outperform a classical computer or a classical way of doing things. Okay. This is called the Deutsch oracle problem. Imagine someone gives you a black box containing a function on 1 bit. I think it is a strange gift, but let's say somebody has gifted you a box with a wire coming in and a wire going out. Okay. One bit. It's a black box. You don't know what it can do. There are 4 possible things it can do, right? What are the 4 possible things? Talked about the last class.
Internet.
What are the 4 possible functions on 1 bit? The identity, the negation.
Zero.
Converse is negation. Constant 0, constant 1. Right? 4 functions that I talked about in the last class. You should try and remember. Okay. Now, you don't know which function is inside the box, right? You can see just the inputs and the outputs. You don't know the 4 functions. Now, the question is, how many queries would it take to determine which function is it on a classical computer? Like, how many queries should you do on that black box to understand what is the function inside the black box? 16. Why 16? Now, see, this is simple. Probably here the people in a class have a little bit of an advantage. I guess I keep telling people to come. I can't do anything more. Yeah. So
4 possibilities for each function.
So 4 possibilities, right? See, what is it? You put 0 here. You can get 0 here. Correct? And another case, you put 0 here, you get 1 here. Correct? So 1 possibility. If you put a 1 here, you can get a 1 here. If you put a 1 here, you can get a 0 here. So how many you should do to understand what function it is? How many times you should run this query? So one query, let us say you run it with 0 first. Okay, you ran it with 0.
2.
Okay, you got 1. Okay, let us say you put 0, you got 1. There can be 2 reasons, right? Either it can be negation or it can be constant 1. You don't know which one of these is the reason why that is happening. Okay, now you put 0. Okay, if it comes 1, you know the answer is negation or whatever. or constant 1 probably. Yeah. Or then you know the answer is constant 1.
2 operations.
At least 2 operations, 2 queries you should do. Right? Guys on the phone, are you getting what I'm trying to say here?
Yes.
Yes, no, maybe, don't know, don't care. What is the answer?
Dheeraj, yes, Anna.
Huh?
Dheeraj said yes.
Dheeraj said yes, very good. So I'm going to take Dheeraj
Yes.
as the representative
Tamachari
of everybody.
yes.
People don't want to talk, is it? The whole generation is different. They will type, they will do whatever, but they won't talk.
So when we put 0, how come we don't get the constant 0 also there?
You can get it. You can get it. So let's say
Four
you.
possibilities for each. That means 4 possibilities for each input.
But you are already giving an input.
See,
What's the
What's up?
If I give 0 here, I can get output only as 0 or 1. Only 2 possibilities are there. No, I can get only 0 or 1. Only 2 possibilities I get. If I get a 0, okay, then what are the 2 answers? Either it is an identity function or it's a constant 0. I don't know which one of those it is. Then if I put another number through it, if I put a 1 through it, if I get a 1 again, I know it's identity. If I get a 0, then also I know it's a constant 0. So I need to have at least 2 queries. Correct? Now, how many do you need on a quantum computer? If this is a quantum computer, how many queries do you think you need to kind of say if this is to determine which function is it? If you want, you guys can come right on the board for 2 minutes, but think about it, otherwise write it on a piece of paper.
Encore possibilities.
Anybody, any answers, any guesses? Come on, man. I can imagine how you guys must have been in your engineering classrooms, okay? Here, when there is absolutely nothing, कुछ भी बोल सकता है, फिर भी लोग they don't want to say anything. That is why those professors become like that. You know, after a while they lose interest in teaching also, and nobody ever responds. I don't know, man. I get exasperated. That's why I'll tell Raja, I'm not a good teacher. I can't teach.
No, it's not about the good teaching. It's about fear of teaching.
No. What is the problem? What?
Telling something.
So say something. I'll say 1, 2, 3, 4. कुछ तो answer होगा. What is the worry? You should see. I'll tell you. In mathematics, especially mathematics and logic, if you don't write and if you don't think, then the subject is useless because you will get nothing out of it. You know, I can say everything that I want, but you'll have to draw. First, take a paper, write down those things, and just see what it is. You know, if this was a quantum computer, what would you have? 1 by root 2, some superposition state you will have. Okay, does it make any difference to your input and output?
No.
Correct? No. So then you still require 2 only. Correct. Simple answer. No. Whether this is classical or quantum, what difference does it make? Because you are sending something, you are measuring something. That will exactly be same. So I'm sorry but this problem, quantum computer does not offer anything. Even if I put quantum here, you still need 2 queries. Clear? This is the other thing about a problem solving. You should think what part of what I said is useful to the problem. I called it quantum. It doesn't make any difference to the way how I solve the problem. How does it matter if it's quantum or not? Okay, it's still the same crap. So, right? Get it? Guys, everybody clear? You will still require 2 queries. Classical also 2, quantum also 2. But I promised you that this will somehow be better. So, let us see if it will ever be better or if it is going to be better. Okay. Now, let us change the question a little bit. Let us say, instead of figuring out what function is it, if I ask you, can you tell me if the function is a constant function or a variable function? That is it constant 0, constant 1 is one class. Identity and negation is one class. Now, can you differ? I don't need to know exactly what function it is, but I need to know whether it is a constant function or a variable function.
Based on the output, I think.
Yes, so the same thing, but now I'm not trying to figure out which one of the four functions it is. I am trying to figure out if this operation or this function in the black box, is it a constant function or a variable function? What is a constant function? Constant 0, constant 1. I'm calling identity and negation as variable functions. That's all. Now I want to find that out. Then how many operations on a quantum computer and how many operation queries on a classical computer? First, how many queries on a classical computer would you need?
One query would be there.
But try it out. I will give people a little bit of time to get to that. Okay, that's a homework. Solve it. It's not very difficult. It's just logic. It's just putting it down. On a classical computer, you would still require 2 queries. But on a quantum computer, you can do it with 1 query, and we'll prove that through the course of the next. Maybe not in the next 20 minutes. If we can't, we'll get to the next class. But we will prove. Okay. On a quantum computer, you can answer this question using 1 query. Just one bit you send, and with the response, you can say whether it is a constant function inside or a variable function. For a classical computer, you still require 2. Okay.
Classical 2.
Classical 2. Quantum is what we will see. We will prove that it is 1, and that is the class of problems. One class of problems that you can speed up with quantum enormously.
If you know one thing, so obviously the other will be known.
And you can solve it hugely. In fact, this in itself may not seem very big, but even your Shor's algorithm, they are built on this fundamental concept. See, it's the way you frame a question, right? If you say the world is divided out of 2 types of numbers, prime numbers and non-prime numbers, how do I distinguish? What's it? The number of queries will be diametrically smaller, very, very significantly smaller in this case, which also goes to what I talked last time about P versus NP problem. Okay, so how you frame that question, and if you can kind of take it, you know, yeah, we'll get there. There are a lot of, it's not just this directly will solve that problem, but this is the core property which helps you get there. Okay, Shor's algorithm, for people who do not know this, you should, is the factorization algorithm, right? Because what is the biggest problem? You can't factorize primes, right? Given a number, can you figure out the factors, prime factors of a number? You can't, right? It's a huge problem. Actually, this is how the theorem goes. Okay, I don't know if anybody is interested. Pi of x, which is known as the number of primes less than a particular value x, when x tends to infinity, will actually tend to x divided by log of x. Anyway, this is the density of primes Euler theorem. We will not solve it, but I'm trying to explain to you why that is so important. Because all of your security, all of your banking security is based on the assumption that you cannot get the prime factors of a large number in any realistic time if you don't know. If I give you a 50-digit number and ask you to figure out the prime factors of those two, it will take you more time than the number of electrons in the universe to actually get to that factorization. You cannot factorize it unless you know the prime factors. But look at the strange thing. If I give you the prime factors, you can easily check. The checking is a 1-minute job, but the reverse you can't. Okay, that forms the entire basis of encryption and cryptography. That forms the basic. You would have read, right? 1024 RSA, 2048 RSA algorithms, whatever, 2048 bit. So that's basically this. It's basically prime factorization. That's all. Given a large number that can be stored with 2048 bits, can I get the prime factors of it? You cannot. And you can get it by luck, but not through an algorithmic process. Okay. Anyway, so we will see. A man called Shor in 1980s proved that using quantum computational methods, it is possible to prime factorize a large number. That's why you also hear a lot of pop news articles, nonsense around saying that once quantum comes, all of your security is gone. That is because but for all his things, Shor could only factorize, I think, 15. The quantum computer that he could build, we could only factorize. So in theory, it is right. In practice, we are nowhere close.
15 digits.
No, number 15. All that he could show was number 15 was the number he could show, okay, which is not a very big thing, right? Everybody knows prime factorization of 15. But the point is, the algorithm works. So if you can build a quantum computer of millions of qubits, then it is possible in theory to prime factorize anything. And that is based on this principle, which we will see. It's called the Deutsch oracle problem, okay? How can it be done in a single query? We can do the magic of superposition. We will define what each one of the 4 functions look on a quantum computer. Right? Before, and we see that we have an immediate problem with constant functions, because constant functions are not reversible. So we can't use quantum functions. We can't use constant functions in quantum computing, right? So what do? We immediately get into a problem. How do we write non-reversible functions in a reversible manner? Let's actually probably. It's so much easy for me to do it on a whiteboard, but no point. Only 4 of you are there. The rest of the world is sitting out there. So anyway, Niku, come see. Okay. So how do we write non-reversible? This is probably the trickiest bit. Okay, in this entire class that I'm going to take. Probably I'm going to take this and I'm going to stop here for today, because this always gets confusing. Common hack: add an additional output qubit to the function which is applied. We just have to rewire our black box in this case. Normally, what is it there? There is some input, there is some black box, and there is some output, right? The diagram that you see on the left hand side. Yeah. What we do, we have to rewire the black box a little bit now to kind of do this. We are assuming we can do it, okay? Otherwise, the whole thing just falls apart. Just assume, just play with me. You add another input wire. Okay. Now the terminology here is very, very unfortunate. If you want, we can change the terminology, but first let me go with what the literature calls this terminology. Okay. You put another wire on the input side. Okay. You call it the output though. You put it on the input side, you call it output. That's what I'm thinking. Terminology is very unfortunate. It's very confusing at that level. Okay. You always pass 0 through that. Through that wire, that input wire, which you call output, you always pass the 0. Okay. Then, so what you're essentially going to do is this. Maybe guys can see it. Maybe guys can. So what do? You have your black box. Okay. You have your normal input, which came out. You add one more thing, and this probably takes X. Okay. You call this output. It's unfortunate, but call it output. You always pass 0 here. Here you have again 2. Okay. This, even though it is output, you still call it input. Okay. Here output, you call it output. So this output is called output even on the input side, and this input is called input even on the output side. Now, here you pass the function, the output of the function, whatever this black box does, through here. And here you pass X only. So input will be X. The output of the input wire will also be X. The input of the output wire will be 0. The output of the output wire will be the original function of X, which should have come through this in the end. So this is how you rewire. Okay. First, understand what I'm saying for a second, then I will run you through examples. Don't worry, okay, to actually explain this, because this is where most people drop off on quantum computing. I don't understand what is going on. Okay, but this is important. Okay? This is very, very important, because it's not so difficult. And it's unfortunate if people just drop off at this level. It's very introductory and it's kind of So you understand what I'm doing? I have a black box.
If there is a simple equation, we just square everything. This whole square is equal to that whole square. And then that makes solving the equation easy. So we are trying to do something.
Yes, that I will talk about. Yes, that's a nice. Exactly, God. Okay. So I don't want. Yeah, I know what you're saying. For example, if you have an equation like 26x square plus x equals 27. If I give you this x, if I give you this equation, anyway, I will talk later because people are waiting. If I get in this, then they will get confused. They won't understand what I'm talking about. Okay. So anyway, so guys, do you at least understand what I'm saying here? We will rewire the box such that we will add two more wires, one on the input side, one on the output side. Okay. We will call it output on both sides. Okay. The input also will be called output. The output will necessarily be called output any which way. And what are we going to do? We are always going to pass 0. The new output wire that I have added will carry the actual function of x output, whichever this black box would do here, whatever function, right? And the input on the output side will carry the identity, will carry the same. Okay. And I am claiming here that if I rewire the black box like this, I can describe your constant 0, constant 1 functions as a reversible function. That's what my claim is in this. Because my problem is I have constant 0, constant 1. They are not reversible. But I have to figure out a quantum way. Okay. And I'm saying doing this sort of madness, I can solve it. Okay. That is my claim. Now, for the next couple of slides, we will see how does that work. Okay.
Sir, are we saying that the input output we are getting, the below one, if it is opposite, then it is not, it is a variable. If it is exactly identity of the given input x, then we can say that this break block having the function constant.
No, I am saying identity and negation are variable functions, both of them. Okay, because identity is what? Give 0, give out 0. Negation is give 0, give out 1. Both of these are variable functions, and both of these are reversible and inverse functions, right? So if I take 0, I put an identity, I put another identity, I still get the answer as 0, right? So it's a reversible and inverse function. So fundamentally, it is a quantum gate. I can use it as a quantum gate. Similarly, negation, same thing, 0, 1, 0. So it is a reversible inverse gate. Hadamard function, reversible inverse gate. Constant 0 is not. If I take 1, I put it through it, it becomes 0. Again I put one more constant 0 function, it comes out as 0 only. So my 1 is lost now. I started with 1, now I have 0, so it has overwritten. Any function that overwrites is necessarily not a reversible function. Only if it permutates is it a reversible function, because I can get the permutation back, at least in theory I can. Is that making sense? Siddharth. Okay. I'm hoping it made some sense to you.
Yes, sir. Yes, sir.
Okay. But Siddharth asked the question, didn't he? Okay. Okay. Let's move on.
He's not. So,
Okay. Now we'll see some examples.
No, I think you got some power misleading.
Or power problem or something, or some other issues. Okay. If you look at constant 0 now, look at this, what happens. If you want to do the constant 0, it is very simple, right? If I put 0 here, what will come out here?
0.
0.
So yeah, it's constantly one query.
I don't have to do anything.
Mm.
If this inside function is const 0, I don't have to do anything. If I just do this, I get the answer. We will see if it's reversible or not. We'll get there, but I'm getting it, right? I'm actually putting 0 here, I'm getting 0 there. There is, if it is a constant 0. Let's see what happens for constant 1. For a constant 1.
Constant 1 is 0 with the 1.
0.
This will be 0. This is 0.
0.
So,
You will put 1. What will you get here?
oh, you're putting 1. 1. Constant 1 this is.
No, oh, okay. Oh, this is constant 1, is it? Okay. So you put 0 here. And this is always going to be 0. Here, whatever you put, if it is constant 1, here you will get
1.
and here you will get xx. Here you put x, you will get x. So if it's a constant 1, you get this as constant 1, right? So finally, what are you doing here?
1, right?
Sorry, what?
In this scenario, right hand side input becomes 1. Is it correct?
Yeah.
It's constant 1.
No. See, constant 1, you are trying to mimic using this gate.
Okay.
See, basically what you have, constant 0 is automatically coming. You don't have to do anything with this gate structure. With constant 1, you have to put one negation between this and this. If you put a negation, you are getting 1. No, always you are going to get constant 1. Clear? Is it clear? If it is constant 0, you don't need to put anything. You constant 1 cheyali ante 0 ki akkada meeru negation oka negation gate pedte you can mimic the actions of 1. Okay.
So all the proving is that we can do a reversible function in quantum number.
Yes, ante for constant 0, constant 1 kuda constant 0, constant 1 also you can write using some reversible gate structure. This is the circus for doing that only. All this circus you are trying to do that. Similarly, if you want to have identity with the same gate, you can do it. You just need to have a C0. We'll see some examples, but I think we should also try it out. Okay. So you can actually do a C0. If you put a C0 gate, you will get the identity function.
So basically, you are coming up with the structure where all combinations can be
done in a reversible way, because normally otherwise we couldn't, right? Because constant 0, constant 1, you can't actually do a reversible because those two are not reversible. So you are trying to come out with this complex structure. This structure will help you write all those 4 functions in a reversible way, reversible and inverse way. Okay, this is actually called this is what is called the Gates quantum model. The name that I talked about initially, this structure is what is called the Gates quantum model. Okay. No, it's not after Bill Gates, it's some other Gates, I don't know.
I thought it was Bill Gates.
No, it is not Bill Gates, it is some other Gates. I don't know who that Gates is, but it's called as Gates quantum computational model. Okay. No, Bill Gates had nothing to do with this. That's some other Gates. Similarly, negation will be a C0 followed by a negation. I think you should try all these out, and I think we should try this out, but this is what the results of those things will be.
Maybe we can play with some
Numbers.
truth tables.
True. You have to put excess zeros. Maybe today we don't have time, but I'll go through a set of examples and do it, because this is important. Because if you don't get this, the next part will get even more difficult. When I'm trying to, like I said, Hadamard gate is required, then this is required. They're the only 2 things where whatever in this introductory course is a little bit complex. Otherwise, the rest of the thing is just a lot of English. And I've tried
As the
to
number of combinations in the
increase,
number of rows will be
increase. And then you have to do more and more and more and more, and you can pretty much create any gate. That is what it is. Yeah, this one I will probably not do today. Okay, let us get to this next time, which is how do we solve it. So homework is I want a truth table from everyone. Go and put a truth table and tell me how this structure puts all of those functions. It won't take more than 20 minutes plus. It's very simple, 15-20 minutes. But just do it once so that you actually understand what I'm talking about. Otherwise, you will.
So if you want to implement all sort of gates.
Just 4 gates. Okay. Just that inverse identity and constant 0, constant 1 using this structure. So for different inputs, show me what that outputs here will be with this structure. That's all. Okay. That's all that there is. Guys, get it? Was it useful today? Have any questions? We have a minute. And the reason I'm sticking to time so much is because I know people have projects and people have work to do. If I just keep talking about it, then it will be fine, but that's not the right way to do it. Okay. Was it helpful? Next class, come with this truth table. I will randomly ask somebody who is joining this class to show it to me. I unfortunately have to become like that. I'll call somebody's name. Okay. So that doesn't mean that people will stop joining. Then also I'll ask guys to figure out who is not joining. Okay. Because I know some smart fellow will think I won't join next class. No, what the hell? How will he catch me? So yes, sab drama mat karo. I'll ask guy. I don't want to get to a state of having attendance and calling people, man. What is this? I don't want to get there. Don't force me to get there. Okay, that's fine. The next time we will actually solve this. How this can be done in one query. But before that, until as you have this clear, there's no point me going through this. Okay. Everybody will nod their head, but nobody will understand. So do the first thing and then we'll do this. Once this is done, we will get to the interesting part probably. We will talk a little bit about entanglement, proper entanglement, quantum entanglement, because that's where things really start getting interesting of what it is that we can do. Okay. We'll also, if the time permits, I'll also talk about teleportation, which is the real science fiction thing. Okay. In time travel and teleportation, we'll talk about those things. But first, get the basic math right. otherwise I can't prove that for you. Okay. Antanama, I think that's all it is. Then yeah, I think all of this is there. But like I said, I don't come with your own truth tables, and then I will go through this whole thing tomorrow.